For alkanes now, we're going to look into some of the properties and applications and where do you find alkanes and all sorts of other things for alkanes. And so what are we going to do here? So first of all, we'll learn about different kinds of carbons and hydrogens that we have in alkane. And if you're wondering what this is, well, we'll go through that. We'll learn about the physical properties, where we find alkanes and applications of alkanes. And by the way, this is something that I do for all functional groups, is that we talk about the naming of that functional group, which we have done already. Then we talk about physical properties and where they are found and applications in whichever order. But the first two are for sure, okay, that we do this. Now, regarding the different number of carbons and hydrogens, okay, so I've been talking to you a bit about connectivity from before, like how things are connected in organic chemistry is one of the biggest things possible because that determines the structure, okay? So it's not just that it's important, it's because of the structural detail we need to know how everything is connected. So carbons and alkanes generally are going to be connected to carbons, unless it is just methane, right, for the first one. So how many carbons are connected to that one carbon is how we classify the different kinds of carbons. And that's what we're going to do now in the next slide. But the way we connect the carbons is also how we connect the hydrogens, because hydrogens is connected to one carbon. But that one carbon can be connected in different ways, okay? And so that's what we're going to look at now. So here's the classification. You have primary, secondary, tertiary, and quaternary, okay? So the short form of that, and you will see that we have a lot of shorthand in organic chemistry because the line structure itself is a shorthand, but we do have a lot of shorthand which helps a lot, okay? So 1 degree, 2 degree, 3 degree, and 4 degree. Those are the shorthands. So what's a primary carbon? A primary carbon is bonded to one other carbon. So that carbon I've made in red, that carbon is bonded to one other carbon, which is in blue. That's called a primary carbon. A primary hydrogen is connected to a primary carbon. That's it. It's as simple as that. A secondary carbon is bonded to two other carbons. So here I'm pointing to the red carbon again, and it's connected to two carbons. And so it's considered to be a secondary carbon. And then secondary hydrogens are the two hydrogens connected to that carbon. So tertiary carbon would be connected to 3 carbons and would have a tertiary hydrogen. A quaternary carbon is connected to 4 carbons now, and it has no hydrogens now. So there's nothing like a quaternary hydrogen, okay? So if anybody says that to you, they're messing with you. Okay, so you have 4 different types of carbons and hydrogens. Well, 4 types of carbons, 3 types of hydrogens. Primary, secondary, tertiary, and quaternary carbons, and primary, secondary, and tertiary hydrogens. So here is an example of how you would classify these things, okay? And if this is a little messy for you, you know, just follow the color coding, okay? That will help you. So the easy way to look at this, okay, is anything that is hanging out, this terminal, that's going to be primary. Because in the case of primary carbon, it's connected only to one carbon. I mean, I could look at it the other way also, right? In this case, because there was only two carbons, that's it. So this carbon is connected to only one carbon. All right. So this carbon is primary and the hydrogens are primary. So that's the terminal ones. Okay. So now let's look at the internal ones. Okay, inside. So the first carbon that we have here, this one is a quaternary carbon because it's connected to 4 carbons. The next one over, this one, is going to be a secondary because it's connected to 1 and then 2 carbons. The next one is a tertiary. This one is a tertiary carbon connected to 1, 2, and 3 carbons. And then the next one is going to be a secondary because this is connected to 1 and 2 carbons. So it's really all about connectivity, okay? And it's really all not that hard. Just kind of focus on the carbon you're looking at and see how many other carbons it's joined to. 1 more primary, 2 secondary, okay? It doesn't get easier than that. So here is a problem, okay, for this. Now in this case, there are 2 things in here that I've covered for you, okay, because this is also an important thing about any kind of a compound, is when you're trying to determine how or what kind of carbons and hydrogens you have, the first thing you have to know also is how many carbons that are connected to. Or if I ask you what kind of a hydrogen there is on this carbon, you need to understand how many hydrogens there are too, okay, on this one. Now, a lot of times it's a lot easy, okay? We make things hard for us. So let me tell you how easy it is to figure out. So if you're looking at this carbon and you're trying to figure out, and we've done this before, okay, is if you're trying to figure out what kind of carbon it is, you look at this carbon and you say 1 and 2 connectivity, right? 2 carbons it's connected to, so it's a secondary carbon. Well, if it is connected to 2 carbons, what are the other 2 bonds on it? The other 2 bonds are going to be the 2 hydrogens, okay, on there. So we did this back in constitutional isomers also, where we tried to fill out all the hydrogens. But again, do that so that you understand how many hydrogens there are on all carbons. Invisible hydrogens are really quite dangerous sometimes, because we mistake for things and we don't write the proper number of bonds and things like that. So, to understand that, it's kind of nice to go through this exercise, okay? So I did go through here with you, and then of course the classification you can do now yourself. All right, let's go over some physical properties of alkanes. And the physical properties of alkanes will do generally 2 or 3 physical properties. One of the most important one is going to be boiling points. Generally, the boiling points will give you an idea of whether something is a gas, liquid, or a solid. Then we talk about solubility, density, and then smells. Okay, so these are some of the physical properties we cover. So boiling points and melting point we cover together because we cover them as a trend. Okay, not exactly what is the boiling point, but what is the trend. So the boiling points and melting point increase as the size of the alkanes increases. Okay, so methane is the smallest one. Methane is actually a gas. And then up to C4, which is butane, then it starts to get into a liquid state. So what are we doing? Gas to butane to liquid, we're increasing the intermolecular forces. Okay, so how are we increasing the intermolecular forces? Those are increasing because of the van der Waals forces. Okay, that's what it is. So since the dispersion forces increase because of electron density, that's all it is. So van der Waals forces is really what's working. I'll write that here also, van der Waals. But anyway, so it's the van der Waals forces that increases with the number of carbons, and so therefore the gas becomes liquids, and eventually what's going to happen is those liquids will also become solids as you get to even higher number of carbons, and that takes a long time. It's like C20 or something like that, then it becomes a solid. Okay, so that's one of the things that happens, and that's only because of increased electron density, which increases the internal dipole, which then increases the intermolecular forces. That's how it is. Then the second thing here is the straight chain compounds. They will have a higher boiling point than the branched ones. Okay, we've done this before in intermolecular forces, but just a reminder again. And here are also some examples for you. Okay. Straight chains will have a higher boiling point. Why? Because they have more surface area and therefore there is more interaction of molecules. Okay, remember intermolecular forces is the interaction between molecules. So straight chain provides that interaction, okay, that you can have. Cycloalkanes kind of go along with the straight chain alkanes. So cycloalkanes are not all that different from, whatever alkane corresponding alkane might be. Cyclopentane, cycloalkane, cyclohexane, these are liquids now, okay, for that thing. So generally what happens is that constitutional isomers will have a little bit different boiling point and melting point. And again, C6H14 shows you because You can have branching. So when you have branching with constitutional isomers, you change the physical properties of that substance. Okay, so very simple, keep it simple, because alkanes don't have anything in them, right? They only have carbons and hydrogens. So it's all non-polar bonding. So the only thing you have to worry about in alkanes and boiling points is what is the size of the alkane and if there is any branching or not. That's it. All right, so let's look at the solubility in water for alkanes. And alkanes are not going to be soluble in water, as the intramolecular force they have is dispersion forces or van der Waals forces, whereas water has hydrogen bonding, which are very different from each other. I mean, if there was dipole-dipole, even then you can say there is some solubility, but dispersion or van der Waals and hydrogen bond is just two poles apart, okay, too far apart to dissolve. So, which means that when you add them together, they will form two layers, okay, of things. So when you form two layers, then we have to talk about density. So density of alkanes in general will increase with molecular weight, okay, due to increased intermolecular forces. So for example, it kind of goes hand in hand with the boiling point, melting point also, because when you have more dense substances, then you have more intermolecular forces, right? Things like that. So density of alkanes will increase with molecular weight, okay, because of intermolecular forces. In comparison to water, the alkanes are going to be less dense than water, which means that if you add them together, then alkane is going to be the top layer. Okay, so which means that alkanes are even less than 1 gram per milliliter because density of water is 1 gram per mil. Okay, so alkanes are very light. In some ways it is sort of a blessing. In some ways it's, kind of, I don't know, and we will talk about the applications of alkanes, but the most common alkane that we use in our life is octanes, which is the petrol, that we put in our car, the gas that we put in a car. We call it gas, but it's really petrol, because when we say gas, for me, gas means it's a gas phase. It's not gas phase, but anyhow, so when we have all these oil spills, which is really a very tragic thing, the oil floats on the water, which, as I said, is a little bit of a blessing, because then what do? I mean, it's easier to clean up if something is on top of the water versus sitting at the bottom of the water, right? Because then you have to get inside and clean up. And you can look up the horrible tragedy that we had about 10 years ago in near Florida. And it was really bad because a lot of the gas was, that was all muck, and also it was very crude. So it had very high density and was sitting at the bottom of the ocean. It was very hard. So offshore drilling, I mean, it's really environmentally very difficult for, both for the company also, and even for environmentalists. It's really very hard. Okay, anyhow, that's density thing there. And regarding the odor, which is the smell, then it's really not that bad. Okay, so if you smell alkanes, you're like, yeah, I can smell something organic, but it's really not all that bad. Like, things like turpentine, or when you fill up your gas tank in the car, it's not a bad smell. I mean, depends. Smells are very personal, so I won't get into that. And then for the sources, where does alkane come from? Okay, most of the alkanes are actually coming from the earth, okay, and they're coming from drilling, all right, which I really feel sad for the earth that we have to drill it so much in order to get energy sources out. But that's kind of how it works. So drilling gives us both kinds of gases, which is the liquid kind and the gas kind. Okay, so the natural gas, which is methane, is obtained through fracking. Now, why do we do this? Natural gas, or methane, is actually a very clean burning fuel. Okay, so it burns very nicely, which means that not a lot of pollutants are released when you burn methane. So it's considered to be like a little bit of a cleaner fuel than the other fuels that we have. But fracking, and I urge you to look through fracking and see what happens in that, okay? And what kind of, I don't want to say torture, but really, what do we put the earth through in order to get methane out? Okay, it's really not that good. And you can look over some news articles from Ohio and Oklahoma states, to see what happens when you do fracking. All right, so You're still getting it from under the earth. Okay, so that's where methane comes from. Petrol also comes from under the earth. Now, when you get it from the land, it's all fine. When you get from water, that's called offshore drilling. We were just talking about that. Both of them are really tough to do. They're not easy procedures, especially the offshore is really very hard to build a whole platform out there, and then the drill, and then to transport. It's all, a big deal. And when accidents happen, it's really a big deal, because then there's a lot of spill, and before anybody can control it, there's a lot of gas that's already been spilled out. And you're most welcome to read through. Every year there are accidents, so every year you can find something to read about, for these kind of gas spills. But that happens. And then there's the transportation also. So not only like where you are drilling is where you're using. No, you're using everywhere. And generally when you transport all these petroleum products, you don't transport them in the purified form. You transport them in crude form. And when the crude form reaches the destination country, they do the purification. Okay, and so they do the distillations, and we'll talk about that. In order to clean up, and bring out the useful parts, that you need from the crude petrol that we have. Generally, all of these processes are very polluting, okay, and they're very dangerous also, because alkane is highly combustible. Combustible meaning that it can catch fire, right? So it burns in oxygen. So it's very dangerous environment to work in, okay, and definitely polluting for sure. The problem though with the extraction is, okay, or getting alkanes, is that the alkane production is not just for petroleum products. It also gives us a lot of other substances, okay, and so you can't just say, okay, well, let's stop drilling, let's all go solar, or let's all go wind. You can't do that, because we get a lot of material from petroleum products for our lives, okay. So all the plastics that we have, a lot of the polymers that are made in our life, your cell phones, a lot of these things are actually coming from materials that we obtain from petroleum products, okay. So it's not just that we are getting it for petrol. There's so many other things, okay, that happen in there. Cracking is a word you will hear only when you hear in the petroleum industry, because cracking is what they do to take alkanes that would not be generally useful to make it useful, okay. So cracking is both ways. So you can take something like a 16 carbon and you can break it apart, or you can take a 4 carbon and join it together. That's a whole other chemistry that goes on in petroleum chemistry. So it's a huge thing, okay. And so petroleum products, it's not just that you have people drilling. No, you need engineers, you need chemical engineers, you need chemists, you need environmentalists, you need safety. So much stuff goes into petroleum products, okay, in there. So the other sources that where you can find all these petroleum products is of course volcanoes, okay, which is a natural production, you can't stop that. And of course cattle also, okay, which is also a natural production. You might have heard about some insane theory that people are going to stop having stop eating beef and all that because they want to stop methane from forming. Well, it's not that at all, because cattle does form methane. It's just the way that cattle is bred that it's very different, So if you have so many cattle in such a small space, then your concentration of methane is going to be very large in that area. So if you spread it out, it's going to be a little bit better. Not that you're going to decrease it, but it'll be humane for the cattle also, for the cattle as well, and then also for for the earth. So as we know, whatever we produce, nothing goes away, right? Matter cannot be created nor destroyed. So whatever we are producing, it's all there. It's all stays there. Applications for alkanes. I've talked about this a little bit here already, but let's just go into this fuel source. This is the biggest use of alkanes. So alkanes, especially the 8-alkane, which is octane, is what we put in our cars. That's the biggest one that we have. It's actually isooctane, and iso should give you pause. It's like iso has the the V structure. It has some branching going on, so it's not just octane. Okay, so it's 8 carbons, but in a branching format. Methane, as we said, is used for as a natural gas. So all the heating that goes on in our homes, or if you have a gas stove, that is all methane. Propane, we know that we use that for, camping or whatever, that's compressed gas. The lighter fluid is butane, so it's a very small amount, it's really not that much. You can see there is no pentane or hexane, okay? Hexane is actually used as a solvent, okay, a lot. But pentane, heptane, and all that, those are generally used for cracking then, so you figure out something else to do with those, because those are not useful as a fuel source. And if you're wondering, why is that? That's just because, when you have isooctane, it has a particular boiling point. Okay, so when you put petroleum in your car and you turn on that ignition, you want your car to start. You don't want your car to blow up. Okay, and to have that very right kind of vapor and liquid equilibrium or balance in your car is only given by isooctane. Okay, so it was after a lot of research that this is what they found. There is a whole other thing to talk about at some point, or you can read it on your own, is about lead in these fuels. It's called the anti-knocking agent, and lead was used in fuel for a long time because it was an anti-knocking agent, which means that it prevented, it actually caused the fuel to burn a lot more efficiently. But the problem with lead is that it also causes very toxicity in especially kids, okay, developing kids, because it's a neurological toxin. Okay, so it does affect adults too, but more so for kids. It took almost about 40 years for the Congress to even let lead out of gas. I mean, it is, for 40 years we were damaging our whatever. Anyway, so it's a really bad situation there. Now we use ethanol in the gas, which also helps to burn the gas very well. Now, one of the things you have to think about is, the sources that I was talking about, we get them from under the earth, but I never really asked you, where does that petroleum come from under the earth also? Okay, and you can think about it if you want to, because there has to be something that was there, okay, because all the earth is actually inorganic. The soil, the rocks, all of that is inorganic. So where is that organic material coming from? So when you think about it, it's actually coming from, yeah, dinosaurs, right? All the dead dinosaurs. Okay, so you can imagine how many there must have been. So when they decomposed, this is what we end up getting. Now, the dinosaurs are not just made of carbon and hydrogen, they're also made of phosphorus, sulfur, chlorines. They have other elements in them too. So when you burn all of that, that's the whole part of purification, right? You get all that stuff out. But when you burn it, you still might have some sulfur and nitrogen and stuff in it. So when isooctane is put in the car, it's not just isooctane, you've got some other stuff in there too, which is why when you burn it, and if you smell the exhaust pipe, and I hope you don't actually do this, but if you're standing on the side of the road and the cars are passing, you will smell that exhaust, fumes. Those exhaust fumes are not pleasant at all, okay, and that's because there are other things burning in there too. So this is really bad energy production, which is why I said methane is very clean. For that reason, because methane doesn't have any other element in there except for carbon and hydrogen, similarly for propane. But octanes are really bad, as far as burning is concerned. So you want them to burn more efficiently. So when I said you put ethanol in there, the ethanol helps to burn it more efficiently into more oxidized products. So you, instead of getting nitrogen dioxide, you get nitrogen trioxide. Dioxide is more dangerous than trioxide. Okay, so that's the whole chemistry that goes behind all of these productions for fuel. And then solvents. So alkanes are used for solvents also, and this is very good because you need to do reactions. So like dissolves like, and so you need, or organic substances will dissolve in hexane. I mean, there are other things too, but it's a good solvent. And then we also use alkanes a lot in our lives, as in wax, and Vaseline. So both of these are solid. So you can imagine how many carbons they have in there. Above 22, 24 carbon chains are there. Okay, so these are very good substances that we use. We can't live without these, right? So very common. Okay, so that's it. The most important thing is of course the physical properties, right? The applications, if you don't remember, it's okay. But I would encourage you to read more about it.